Hey, people. Yeah, I'm still here. Let's begin a new unit, and this unit is about forces and Newton's laws of motion. Some people call this dynamics. We call it statics also, depending on the specific phenomena that we're talking about. But it deals with what objects do and why. Here's an object, and as we're looking at it, you'll notice we see all we see is there's an object. I mean, well, we're looking at it at some instant, and what I am, well, I don't know. What do it do? Well, it depends. But what I want you to notice is that nothing is happening to this object. This object is not interacting with any other objects in any way. And that's another way of saying there are no forces acting on this object. I hear you saying, what about gravity? Well, you don't use that voice. But you'd say, hey, what about gravity? Uh, so, um, but let's pretend, for example, that maybe we're in a part of the universe where the gravitational field strength is so weak that this thing doesn't experience any net gravitational force, if there's theoretically such a place. Or let's pretend maybe that it's on the floor of a room and there's a gravitational force pointing like down into the screen, and we just can't see it from this perspective. So for all intents and purposes, let's say no forces acting on the object. Well, what will the object do? That depends. All right. So check this out. Make like a little process chart, right? Was it moving? Well, if it was moving, it keeps moving. If it wasn't moving, it stays still. Now, it keeps moving. Important. In the same direction it was moving in, at the same speed it was moving at. It's Newton's first law. I've heard this before. Objects at rest tend to stay at rest. Objects in motion tend to stay in motion. But let's qualify this. And then there's an until of a blah, 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 blah. So as long as this thing is not acted on by any forces, it'll keep doing what it was doing before. All right? Or how else can we say this? If something keeps moving in a constant direction at a constant speed, we can say this is the same thing as saying it will maintain a constant velocity, which is the same thing as saying it won't accelerate. Okay? That's Newton's first law. It deals with cases where there aren't, well, sort of like saying there aren't forces acting on an object, but we can get a little more, we can look a little deeper into that. I don't know if you can hear what's going on here, but there's some serious business. Okay. Well, what will this object do? Well, let's talk about a case where there's a force acting on the object like that. How big is that force? Well, I haven't defined a scale, but it's not zero. And that direction, does that mean south of west? No, I don't know what direction that means, but it's that way. What will that object do? Well, the tendency people have here is to say the object will go, it'll go that way. Well, that's not entirely necessarily the case, but what this object will absolutely do is accelerate in the direction of that force. It will accelerate in the direction of that force. Now guess what? That does not mean that it's going to speed up necessarily. Because acceleration doesn't mean speeding up. It means, well, it could mean a bunch of different things. One of them might be speed up. But in general, the only thing you can definitely say when posed with this diagram, there's an object, there's a force acting on it that way, that object will accelerate in that direction. Done. Okay? Okay. Now, yeah, how do you know? How do you know what an object will do? Well, it certainly depends on what's happening to the object. Here's case one, and I'll say no forces at all. This object will maintain a constant velocity. Fair enough. What about this one? Well, this will accelerate that way. What about this one? There's a force this way and a force this way. I'm trying to indicate that those two forces are the same size. Well, guess what? This one will also maintain a constant velocity. What about this one? What about if we did like that, F1 here and F2 there? Not the same size force. Well, this one will accelerate in the direction, in this case, of the bigger force. You know, maybe that's better. Yeah, accelerate that. So what determines if and how an object moves? Well, it's what we call the net force. We have to look at what's the net force acting on an object at any instant. Net, same as saying total or sum of all. You have to look at the combinations of forces acting on objects, and that is entirely what dictates if and how an object will move. Okay? Okay. So here's some objects that don't accelerate. All right? Don't accelerate, which means, well, the net force, the sum of all the forces, the total force on an object is 0. We can write that like so. That's a sigma. Means add up all the, that says forces. Add up all the forces, you get nothing. Now, there's a couple ways we could do that, right? You could just have the case over here of no forces at all. Parentheses. That object doesn't accelerate. Here's another case. You could have a force like that, and you could have a force like that. Are they the same size? Not really. Oh, watch this. You don't think I can make them the same size? You're dead wrong. Turn it around. Oh, what's up now? Okay. So if these forces are the same, same size, there's a case where the net force is 0. There are an infinite number of ways to do that. All right? But we got to come up with a, if we want this condition to be met, that an object does not accelerate, We have to make the net force 0. Another way of saying that is objects that don't accelerate, objects upon which the net force is 0. These are objects in equilibrium. What does equilibrium mean? It means a net force of 0. What happens to things that are in equilibrium or that upon which a net force of 0 acts? Well, they don't accelerate. So what do they do? What must they do? What must these objects do? They must do two things. One, maintain, well, you know what? 0. They must maintain constant velocity. Constant? No, just constant. Velocity. Now, what does that mean? It means two things. Constants, they have to have a constant speed. And they have to move in a straight line. They can't change the speed they're moving at or the direction they move in. Now remember, right, this speed could be 0. Staying at rest is maintaining a constant velocity. Okay? So what's kind of interesting is you can, well, two things. First of all, if an object is moving and you don't do anything to it and you don't push on it, it keeps moving. It doesn't take any force to keep objects moving. I can hear you, Ross. But doesn't it? What up, isn't it? It doesn't take any force to keep objects moving. There's a better way I can say it. It doesn't take any net force. It doesn't take any net force to keep objects moving. Once objects are moving, they just keep moving. As long as they're in equilibrium. It also says that we can be pushing on things like this, and they'll just keep moving in whatever direction they were moving before. So this object could be, I don't know, like moving that way, have a velocity that way, and we could push on it like that, and it would just keep moving that way. All right? Whoa. Now here's an object that's not in equilibrium. There are a billion ways to do this, but you know, what if we were to say like there's a force this way on something of 8 newtons, sure, and there's a force this way on this thing of 6 newtons. Well, that object, hopefully, clearly is not in equilibrium. What? Yeah, not in equilibrium. The net force on that object is not 0. And in fact, based on the presence of those two forces, this object would behave in the same exact way, which is to say, there's the same exact net force acting on this object. Ten newtons. 6, 8, 10, 3, 4, 5, triangle. What I've done is take, hang on, sort of. Yeah, you get it? This 10 Newton force is the resultant of those 6 and 8 Newton forces. This happens to be something, yeah, like a 37-degree angle. Prove it if you'd like with trigonometry. All right, so this 10 Newton force pointing at a 37-degree angle up to the right there is the same exact thing, or makes an object behave the same exact way as if an object had two separate forces of a 6 Newton upward and 8 Newton rightward force. Oh, you know what? The unit N stands for Newton, the metric unit of force. It doesn't mean north. All right? So, let's say we have this same old object here with a 6 Newton force this way, and then, that'd be longer, an 8 Newton force that way. Let's put this thing in equilibrium. Well, remember what we said? Here's the net force right now. The net force currently is 10 newtons up and to the right at an angle of 37 degrees. So if we wanted to put this object in equilibrium, one way to do it is to add a force that goes like that. If the 6 and the 8 Newton force are equivalent to one 10 Newton force that goes that way, and we want this thing to have a net force of 0, well, we got to add one force that counteracts this resultant of the 6 and 8 Newton force, and that's a 10 Newton force that points down and to the left at 37 degrees. That object with these 3 forces on it is in equilibrium. The nice thing to see here is things in equilibrium don't just have to have, a force this way and a force that way where the 2 forces are the same size, or they are what we call equal and opposite. It can happen in literally an infinite number of ways. And, sometimes there's, a certain force pointing, in one direction, and a different force pointing, and then even a third totally different force pointing. But as long as they add up to 0, the net force is 0, and then the object's in equilibrium. And guess what? This object behaves exactly like this object. I'm done. Behaves just like an object with no forces acting on it at all. It does the same exact thing. It maintains whatever velocity it had at the instant before we started looking. Okay? Okay. Now, objects that do accelerate. That means there's a net force acting on them. What we call a non-zero net force. So here I'm just going to say that net force is not 0. That's equals not 0. And this is still the sigma, just a little bit sloppier. I'll make it neater. Fine. So objects that do accelerate have to not be in equilibrium, which means the net force acting on them is not 0. Well, there's certainly an infinite number of ways to represent this, but what I want to sort of look at is, let's assume for a minute that v0, these things' initial velocity, is toward the top of the page. First of all, velocity is not a force. So there's no, the force of the object's movement, there's no such thing. The force of its velocity, there is no such thing as that. That's not a thing. Velocity is velocity. Force is force. They're totally different quantities measured in totally different units. They're both vectors, so we can represent them both. I'm saying, now this thing's moving this way, but what I don't want to do now, I know we did it, a ton of it, in projectile stuff and trajectory stuff, is say, here's its speed. But now, anytime we draw vectors sort of coming from an object or ending on an object, those vectors are typically going to represent forces. All right, so let's say that, all right, we're just going to say it. These objects are all moving toward the top of the page. Well, let's also put a force pointing toward the top of the page. You know what this one does? I know you do. Well, first of all, we know, one, this thing accelerates that way in the direction of that net force. And therefore, I don't know what the 1 is for. This thing accelerates that way. Remember, it was also moving that way. So this thing speeds up. Yes? Sound familiar? I hope so. Now this one. This one is still moving toward the top of the page, but there's a force pushing that way. Well, this one accelerates downward toward the bottom of the page. And therefore, what does this object do? Well, it was moving toward the top of the page, but accelerates that way. That makes this thing slow down. Here's an object moving toward the top of the page, but there's a force acting on it like that. Well, one thing for sure is it accelerates to the right. But you'll notice that this force has no component that points in the direction of motion that would make it speed up. It has no force that points opposite the direction of motion, which would make it slow down. So this force, at this instant, when the thing is moving upward but being pushed in a direction perpendicular to that, can't change speed. But it does accelerate without changing speed. And that's why it's real important to remember that acceleration, first of all, doesn't mean speed up. Second of all, doesn't mean change speed. Accelerate means, it doesn't even, but it's closer to, it doesn't even mean change velocity. Acceleration is the rate of change of velocity. That's being a little bit picky. But this thing, if it accelerates, will change velocity without changing speed. That means it must and can only change direction. Okay, so acceleration can be manifested, I don't know, might be too fancy, can happen in 3 different ways. Things can speed up, things can slow down, things can change direction, and it depends entirely on how forces and the direction of forces compare to the direction that an object moves. Okay? Okay. Now, for us, what will be pretty common and certainly convenient is in a lot of cases to talk about components of forces that are in convenient directions. All right? And we'll deal with lots of questions like, all right, there's an object on a table, and it's moving across the table. Or there's an object, that's being picked up out of a, from a rope that, sure, is pulled upward, right? So, if there's a force like this that's not in the direction of that motion, or it can be more convenient for us to do something like break forces up into perpendicular dimensions. This should look pretty familiar because we have spent a lot of time breaking velocities up into perpendicular dimensions. Now we're just saying this is a different kind of vector. It's a force. Well, remember, if we want to find the x component of a force, that for us would be f cosine theta. Y component of a force, f sine theta. If that's like totally Greek to you right now, that's not good. I'll be blunt. Hopefully that's not too new. Okay, there? Okay. Yes. Now we get to what most problems in this unit look like. Finding force in finding net force, I should say, in 2 dimensions. And what will be important is typically to find the net force in each of 2 dimensions. And those 2 dimensions are in most cases what we call the x and y directions. Right? So in most cases, in most problems, and you're about to get a bunch of practice with this, what you will write are what are called net force statements. And you'll do a net force in the x direction and a net force in the y direction. And so I've just defined for you our coordinate system. X means horizontal, y means vertical. And typically, really, for the rest of this unit, I'm going to do this. I'm going to say that to the right is the positive x direction. Upward is the positive y direction. Here's the negative y direction. Here's the negative x direction. Okay, and so let's say, for example, that the following force acts on this object. A. I thought it's force, F, whatever. I'm just calling it force A. Well, okay, well, the net force apparently is A in the horizontal direction. And so far, I don't see any forces that point up or down, so the net force in the vertical direction is nothing. Yeah? If I were to say, do this, well, the net force in the y direction now is B. But the net force in the x direction is still just A, because B doesn't have a right or left component, right? What if I did, I don't know, let's add another force C. Now, even though this kind of command is add up all of the, I'm going to write that as the new net force in the x direction is A minus C. Really what we're doing is saying A plus negative C. Because C points in the opposite direction of A, so it wouldn't be, if A was 30 and C was 15, it wouldn't be right to say the net force is 45. The net force would be 15. Okay? How about this? What if I were to do that? There's nothing special about that length. Here's force D. Well, so where does force D go? Does force D go in the x direction? Does it go in the y direction? Well, it doesn't go in either. What's the most appropriate to say is that it has components in each of those two perpendicular dimensions. So I would now say, let's see, the dx component points to the right. I'd add dx. The dy component points down. I would therefore subtract dy. And if we went one more step and defined that d pointed at that angle relative to the horizontal, the one more step we could go through here is to say this would be d sine theta. Excuse me, this would be a minus c plus d cosine theta. Yeah? What do you think? This is the crux of being able to do this, identifying different forces, and being able to figure out, is that a horizontal force, a vertical force? Does it point in the positive direction, the negative direction? Does it have components that point in different directions? And being able to add them effectively is the crux of the entire unit, this entire unit. Okay, and writing these what are called net force statements is really the crux of the entire unit. Okay, however, forces aren't really just A's and B's and C's and D's. They're actual real forces out there, and there's 5 of them that we're going to start with. And I use an acronym / mnemonic device. Not really mnemonic device. WANTF. When you're drawing what's called a free body diagram, which is a representation of all the forces acting on an object, you want your forces. You want to make sure you identify all the forces that act on an object. And conveniently, well, there's one of them that starts with a W. Weight. And weight is the force applied by gravitational field. Force applied, force applied on any object, ungroup, ungroup, yes, on any object. By gravitational field or fields. All right? Or some people just say the pull of gravity on an object. Fair enough? Fine. And then, let's see, A. Applied. That's what we call an applied force. All right? And that's a force of one object pushing on another. Just think push. When you hear applied, or when when something insinuates that something's being pushed, you call that an applied force. And oh boy, and now this is called a normal force. And a normal force is the force that any surface exerts on an object. On an object. Next is T. Tension. That's a force that any string or cable or wire or rope exerts. I want this to be one line. Is that so much to ask? Think pull. Something's being pulled, that's a tension. Right? We said think push for an applied. Think pull for a tension. Okay, and last, it's friction.
Please pardon the interruption for a couple of announcements. Today's JV
Sorry.
football game has been moved.
Now, friction forces are also a force that a surface exerts on an object. But only, I'll say, but only in response to motion or intended motion. I'll tell you more what I mean about that in a minute. So yeah, you're all familiar with friction. And friction happens if things are moving, but sometimes happens if things otherwise would move if friction wasn't there. Sometimes friction keeps things from moving, keeps things from moving at all. All right, now this normal force, notice it says normal force is a force that a surface exerts, and a friction force is also a force that a surface exerts. So the normal force we should qualify a little bit. So if the friction force is exerted in response to motion, the normal force is exerted in response to the object pushing on the surface. So here's the deal. You ought to see me right now. I am leaning against the wall like you read about. I'm literally, I got my arm out. I'm pushing, well, if the wall wasn't there, I'd be falling over. So I'm pushing on the wall. And because of that, as a reaction, as a response to that, the wall pushes on me. I'm standing, well, heck, without even leaning on the wall, gravity is pulling me down onto the floor. So I am pushing down on the floor. Well, in response to that, the floor pushes up on me. So anytime an object pushes on a surface, the surface pushes on an object. That's what normal forces are. Okay? So you need to have these 5 forces. Well, we're going to get some practice using them. Okay? All right. There are 3 forces that there's some specific rules about. And they have to do with the directions that forces push. And one of them is weight. For us, we're always going to represent weight forces, almost always, for the foreseeable future at least. We're going to say that weight forces always point straight down. Come back later. 5 minutes. Jack DeRizza. Always wanting more. Always give me more physics, Mr. Warner, more. Always point straight down. Now, what do I mean by that? I don't really mean straight down, but what I really mean is toward the center of Earth. But typically the way we draw things, we're just going to draw weight forces straight down. Okay? Normal forces well, here's a representation of an object on the floor. All right? Well, in this case, gravity pushes or pulls this object that way towards the center of the Earth, and that happens to pull the object down onto the floor. And so therefore, the normal force points up. Now, N here means normal force. You want to write F subscript N, fine. Please don't just write G, because that means acceleration due to gravity. That's the one that I do as F subscript G. Here I mean normal force. All right? But check this out. Here's me leaning on the wall, relaxing. Yeah. There's 2 normal forces acting on me. One, there's one like this, the normal that the floor exerts. Since gravity pulls me down onto the floor, well, the floor has to push up on me. But there's also a force here. Since I am pushing against the wall, that means that the wall pushes on me. But the bottom line is, these normal forces are always perpendicular to surface. Okay? And third is a friction. Friction, well, here's an object, oh, I don't know, say that's sliding down a hill. Or maybe it's not sliding. And the only reason it wouldn't slide is if there was friction. So if it's sliding down the hill, or if it's not sliding, that means that friction force, and that's one that I always use a subscript with also. If you just write F, what are you saying? Just force? So I use the friction force, or force of friction. All right? So friction forces are always parallel to surfaces. Of surfaces. And yeah, there's some weird friction examples. But typically, what you think about is if an object's moving and something doesn't say frictionless, well, there's got to be a friction force that opposes that motion. And sometimes things don't move because of friction. And then you'd say, well, what direction would they move if there wasn't friction? And then sometimes friction actually is the only thing that makes an object move at all. And then things get a little wacky. All right, but those are three. There's no rules about what direction things are pushed. You can push something in whatever direction you want. There's no rules about what direction a string would pull on something or a cable would pull on something. So those are whatever you want. But these three have rules. All right, so just be careful to make sure you apply those rules. We're going to get some practice next time with drawing these specific 5 forces as they are applicable to objects in lots of different situations. But this is a good intro into all the stuff we'll need as we go forward. Okay? Farewell and adieu.